It's out there, right now, hurtling through the darkness. We can't see it, but a rock the size of a skyscraper is headed right for us, moving at 50 times the speed of sound.
This is serious stuff now. It will happen, and when it does, you want to be prepared.
Asteroids have decimated life on Earth before. They'll do it again, unless we stop them.
The dinosaurs went extinct because they didn't have a space program, right? We have that advantage.
Across the globe, scientists and astronauts are gearing up for a cosmic battle to hunt asteroids, to capture them, and to shoot them out of the sky. We think of space as a silent void, but the universe is a violent place. Black holes spew out deadly blasts of radiation. Solar flares explode millions of miles into space, and rocks as big as mountains careen into planets, moving at 10 miles a second. It has happened here before. 65 million years ago, an asteroid 6 miles across wiped out the dinosaurs. It can happen again. A chunk of space rock, just a fraction of that size, could kill millions. On February 15, 2013, the universe sent us a warning shot. An asteroid just 60 feet across exploded in midair over Chelyabinsk, Russia. Thousands of people were injured.
People went to the windows to look up to see the trail in the sky. Then moments after, the shock wave blew out the windows and, cut people's faces. It's the very human story of that event that makes it real for us, that this is why we study asteroids.
Dan Durda is a planetary scientist at the Southwest Research Institute who has been tracking asteroid impacts around the globe. He listens to a network of sensors designed for earthquakes and unauthorized nuclear tests, and the news is not good.
Those detectors have told us that over the last, dozen years or so, a couple dozen, city-affecting impacts have happened across the planet.
Most of those explosions happened over the ocean, Antarctica, or other deserted areas. But with Earth's ever-growing population, the chance of these football field-sized rocks striking inhabited areas keeps getting bigger and bigger. It's vital that we predict what damage these space rocks are going to do. Size matters most, but the next critical factor is the angle at which they enter Earth's atmosphere.
The angle is important from the amount of damage that can be done on the ground, because objects that strike more vertical to the surface of the ground can make it deeper into the atmosphere.
When an asteroid hits our atmosphere, it starts to burn up. Smaller rocks can only last so long before they overheat and explode in midair. The steeper the angle they enter the atmosphere, the closer they can get to the ground before they blow up, and the more damage they cause. But accurate predictions of the damage caused by different angles of impacts don't yet exist. Today, Dan is at an explosives test facility to try to find out. He'll begin by recreating the force of the explosion of the Chelyabinsk asteroid. This 200-gallon air cannon can recreate the power of that blast wave as it hit the city in a localized zone about 20 feet in front of it.
Okay, 3, 2, 1. Oh, yeah.
The Chelyabinsk asteroid came in at a low angle of 19 degrees and exploded at an altitude of 76,000 feet. By the time the shock wave traveled 15 miles to the ground, it weakened significantly. It was not powerful enough to shatter the reinforced laminated window of a car. but it was powerful enough to blow out the plate glass windows on over 7,000 buildings in its path, which is how most people got injured.
In a lot of ways, we got lucky with Chelyabinsk. That asteroid came in at a very glancing angle through the atmosphere, only about 19 degrees or so above the horizon. And that's not typical. Most asteroids will encounter the surface of the Earth at a steeper angle, more like 45 degrees.
If the Chelyabinsk asteroid had come in at the more typical 45-degree angle, Dan calculates it would have exploded at just 40,000 feet. And the pressure of the shock wave hitting the ground would have been about 10 times greater. To see what that damage looks like, Dan cranks up the pressure on the air cannon.
You're good? Okay. Okay, got it. Okay, here we go. 3, 2, 1. Wow, look at that. Yeah, this is pretty bad. This is a heavy dummy, and it just flailed like a paper doll. That's you've at the very least fractured and dislocated that shoulder. We've got windows blasted out. We didn't see that at Chelyabinsk, but had that happened at a more steep angle and we achieved these kinds of overpressures, this is the damage we would have seen. This is not good.
To calculate the total number of casualties a steeper angled impact could cause, Dan needs to see what happens to people inside buildings. What kind of protection would they have? This test office is constructed with an exterior cinder block wall and a standard plate glass window.
Okay, here we go. Ready, 3, 2, 1. Geez, that's incredible. This is what you would see. This is what you would see. There'd be paper flying. There is no office anymore. It's gone. We've actually displaced a cinder block from the wall inward, and it's landed in where our dummy was actually sitting. Take a look at our dummy here. It's literally knocked his socks off. We almost certainly have a fatality. This is horrible. There's one of your shards of glass impaled in the solid wood wall. You don't want to be a part of something like this. This is what we want to prevent.
If a 60-foot asteroid traveling at a 45-degree angle blew up 40,000 feet above a major metropolis, tens of thousands of people could die.
The real Chelyabinsk was a wake-up call, but for me personally, standing here and watching this it makes it even more real than that.
To prevent this kind of devastation, we have to find the asteroid long enough before it strikes so we have time to react. And that's not easy.
Of objects in the size range of the Chelyabinsk impactor, well, we've only found about 1% of those so far. And we think that there could be hundreds of thousands to even millions still out there that remain to be found. The trouble with finding really tiny asteroids is that they're hard to see unless they're very, very close.
NASA has issued the Asteroid Grand Challenge, seeking ideas from scientists worldwide to help find and track hazardous asteroids. Two people who answer the call are former astronauts Ed Lu, who flew on the ISS, and Apollo 9 veteran Rusty Schweickart. Together, they head up a venture called the B612 Foundation.
The actual deflection of an asteroid is the easy part. The hard part is finding them first. And you cannot deflect an asteroid that you haven't found yet.
We've got about 11,000 near-Earth asteroids that we know about now. The next step in finding the remaining million objects that can do serious damage if they hit the Earth is to get a telescope into space.
Looking for near-Earth asteroids is challenging because they are small and dark, and ground telescopes can't pick them out from the blinding glare of the sun. B612 plans to get around that by sending a space telescope into an orbit closer to the sun and turning it around to look out with the sun behind it.
We're going to be launching an infrared space telescope, and it will look out at the Earth's orbit and basically pick up all the asteroids of significant size that cross the Earth's orbit.
Even though asteroids are dark, they absorb heat from the sun and glow in infrared. B612's telescope, called Sentinel, will be fitted with super-sensitive infrared detectors to pick out that glow. But right now, B612's biggest challenge is finding donors willing to pony up the $500 million needed to launch Sentinel. That has Rusty and Ed crisscrossing the country, looking for people who want to save the planet.
My goal tonight is to give people a sense that we as humans can actually change the course of the entire solar system such that this planet is no longer hit by asteroid. This is a current map of all the known asteroids. What Sentinel is going to do is to increase this map by a factor of 100. Using this dynamic map, you will be able to know when, where, and which asteroid is going to hit the Earth and where they are at any given point.
While Ed is hitting up Silicon Valley moguls, Rusty is courting the entertainment crowd in Hollywood with the help of indie rock duo Broken Bells.
So with your help, we're going to end up seeing the continuation of life here on this planet off into the distant future.
B612 has already raised enough money to start designing Sentinel. If it gets what it needs to launch it, the asteroid survey will be complete by 2024. But Sentinel has its limits. It could find 1 million asteroids. Keeping track of them all, however, is another matter. A Chelyabinsk-sized asteroid might change course and cause devastation. A team of hackers thinks it can save us by building an army of space probes designed to track killers lurking in the dark. Up there in the darkness, 1 million chunks of space rock threaten the Earth. Each one is capable of devastating a city and killing tens of thousands of people. If we're going to avert this disaster, we need to track every single one of these objects.
For potentially hazardous objects, we really want to understand their orbits. We need to know the orbits because we need to be able to predict impact events in the future.
The space-based telescopes, or even ground-based telescopes, have limited time that they can spend looking at an individual asteroid. And then the other problem is the orbit of them could change because of interruptions from the moon or from Earth.
Matt Reyes has a radical idea of how to keep tabs on 1 million asteroids with millions of separate space probes, each smaller than a credit card, deployed like confetti to keep watch on Earth's cosmic neighborhood.
So this is the world's smallest spacecraft, and we're using this to reach out to the maker community to help tackle one of the most important dangers that this planet faces, which is the risk of asteroids hitting the planet.
Matt has set up a new spacecraft prototyping facility at NASA's Ames Research Center. He's building microsatellites called chipsats, which are hacked together from components normally used in smartphones. Today, Matt and engineer Andy Philo are making a chipsat that's specially optimized for asteroid tracking. They etch a circuit path on a copper substrate and add a standard issue cell phone communication chip. They then add solar cells to power it in space and an antenna to allow it to beam signals back to Earth.
What we're really interested with this prototype is understanding how strong the radio is and how these antennas are going to work, because we're going to listen to them with a smartphone. So you take pretty much any cell phone, and then what we can do is turn it on. Yeah, and it works. And you can see here the actual spectrum of the satellite chirping.
Chipsats are not launched one at a time like conventional space probes. They go up in batches of 130, deployed from a small spring-loaded device called a CubeSat.
So this is the CubeSat deployer, and there's a spring-loaded mechanism, and when the time is right, the spring will fire out these chips. But in microgravity, what will happen is they will all spin away even direction and scatter so that they become a large array of sensors.
Whenever an asteroid is discovered passing dangerously close to Earth, Matt's team will launch a CubeSat to intercept it, which in turn will deploy a cloud of chipsats around it. That cloud will stay with the asteroid as it orbits the sun. If its course gets deflected by a close encounter with the moon or Earth, the ChipSats will know about it instantly. Some ChipSats will fail, some will drift away from the asteroid, but those are all acceptable losses for Matt. After all, each one costs less than $20.
ChipSats are so inexpensive that we can launch many all at once, and we can deploy them to several different asteroids to track them at all times.
Before they can send them out into deep space, Matt and his team have to test the basic ChipSat technology in low Earth orbit.
So the first flight of the ChipSats are going to be launched off a rocket heading to the International Space Station launched by SpaceX, where it'll be ejected out the side before the rocket gets to the space station, and it'll be on its own orbit and under its own control.
Matt and Andy are joined at Kennedy Space Center by Zach Manchester from Cornell, the creator of the first flight-ready ChipSat prototype.
So the CubeSat is right up there just under the American flag. Right in there. It's actually at the back of the upper stage.
And about how long after launch, after it leaves the launch pad?
It takes about 10 minutes to get up into orbit, and then after that, they're going to separate the Dragons, and then they're going to deploy the CubeSats.
You know, blood, sweat, and tears of a year and a half now come to fruition.
With this launch, the race to save humanity from asteroid Armageddon will begin in earnest.
Oh, yeah, there you go. Oh, okay. Oh.
10 minutes after liftoff, the CubeSat makes a perfect separation from the SpaceX rocket. But 12 days later, disaster strikes. The sun spits out a huge solar flare, and a radiation spike causes the CubeSat's clock to malfunction. It fails to deploy the ChipSats. It's a bitter blow for Matt and his team.
So the CubeSat did burn up in the atmosphere before the chips could be deployed.
But thanks to the low cost of the chips and the fact their launch can piggyback on a space station resupply mission, the Space Shop team will get another chance before long.
We've got the support of Cornell and NASA to reboot this mission and have a second one come up very soon.
For the time being, efforts to find dangerous asteroids are still stuck on the ground or on the drawing board. And even if we get them into space, that's only a first step. We have to design a means to stop an asteroid from plummeting to Earth. Now, for the first time, we are preparing to do just that. Capture an asteroid. They can move at 40,000 miles an hour and weigh upwards of 10,000 tons. The race to defend Earth against city-killing asteroids has NASA scrambling to pull off its boldest mission in decades. It's the craziest thing the agency has ever tried, to capture an asteroid in deep space and drag it off course.
It's a mission called the Asteroid Redirect Mission. And the robotic mission's job is to go out and rendezvous with an asteroid.
At the Jet Propulsion Lab in Pasadena, Chief Engineer Brian Muirhead is developing the technology for snagging a space rock. And this is it, a giant inflatable bag.
This is a fifth scale model of a capture system that's intended to capture a whole asteroid. And that asteroid could be as big as 10 meters and as heavy as 1,000 tons. And the reason it's in a bag is because we don't know about the composition of the asteroid itself. We don't know how well it'll be held together. So we could pick it up with manipulators, but we've chosen a bag to do that.
Before the robotic spacecraft can bag the rock, it has to match its speed and rate of spin precisely.
We expect the asteroid will be spinning, tumbling in some way. So what we'll do is we'll match our spin state with it. So it'll look like there's really no relative motion. And then we'll fly right up to it, and then we'll start the process of closing our bag. So think of it like the cinch on a garbage bag, that sort of idea.
Once the asteroid is in the bag, the spacecraft will fire its engines and start pushing the asteroid off course. If NASA is successful, it will have proved that it can redirect asteroids almost as big as the one that hit Chelyabinsk. But that's not the only reason for the mission. NASA wants astronauts to study their prize up close. We think of asteroids as giant rocks, but that might not always be the case. Some might be nothing more than loose conglomerations of stones, barely held together by gravity. Others might be super dense lumps of nickel, iron, or cobalt.
A lot of factors go into determining how hazardous a particular object is. What is the total impact energy that it could potentially have? That depends on its composition, its density, how porous it is on the inside. Is it a pile of gravel or is it a big lump of metal? How much does it spin? All of these are things that we need to know about asteroids in order to take appropriate action if we ever find one that's on a threatening course.
After about a year of cruising along with its captive rock, the Asteroid Redirect spacecraft will arrive at the moon and park there. Then, for the first time in 50 years, NASA will send 2 astronauts beyond Earth orbit. They'll rendezvous with the spacecraft and its quarry. And then, 250,000 miles from home, they'll venture out into deep space. Clambering down the side of the robotic ship, they'll open the bag and attempt to retrieve a sample of a 4.5 billion-year-old rock. One false step, and they will float off into space with little chance of rescue. It will be the most dangerous spacewalk in history. Today, 2 astronauts are beginning the long process of training for it. This is NASA's Neutral Buoyancy Lab near the Johnson Space Center in Houston, Texas, the world's largest indoor swimming pool and the closest thing to zero-G on Earth. Astronauts on the space shuttle carried 2 suits, one to wear inside the launch for re-entry and one called the EMU for spacewalks. They won't have that luxury on this mission.
For the mission that we're going to the asteroid, we don't have a whole lot of room in the cabin, and we aren't able to take an EMU. It takes up too much room.
Instead, they are going to repurpose the space shuttle's launch and entry suit to make one multi-purpose suit. The problem is that it was never designed for spacewalks.
This suit is a pressure bag, and so every time you move your arm, you're moving against the pressure and against the force of that suit. It wants to stay in one place. And so every time I move my arm, I've got to really put a lot of effort and muscle into that to move the suit.
The objective today is not whether it's the most comfortable thing we can get, it's whether could we possibly make this work with a lightweight suit.
Watched over by a team of divers, astronauts Stan Love and Steve Bowen begin to acclimatize to working in a less than ideal suit.
Nice looking suit you got there.
It's the two-tone thing. I think it's a big thing.
It is. It's good. It makes us look like traffic cones.
Yeah, so the orientation is a little bit different than the EMU.
The first step is to get out of their capsule and grab onto the asteroid retrieval ship. To avoid floating off into the void, Stan and Steve use a short pole.
Let's have both decrease. Here you go. That boom's not quite as snug as it was the last time you saw it. Very difficult. I'm gonna give that a 5.
There's a large stability boom that will be deployed that the astronauts will crawl out onto. They will use that to stabilize themselves so that they can do some tasks like hammering.
Am I doing that, or is the diver doing it?
Somebody's doing it.
Holy cow. That is a mechanical disadvantage, folks.
Today, they are practicing how they might chisel off a fragment of the asteroid. Using a hammer in a spacesuit is surprisingly hard.
Yeah, so the hammer's going up toward your faceplate, just taking up your envelope there.
The only place I can get the 2 of those together is in a square about 5 inches wide and 8 inches high in front of my faceplate.
I agree with Stan's comments. Definitely needs some improvement. We have to think about how we want to do that task.
The difficulty of hammering into a solid asteroid has mission engineers worried.
We had the idea that maybe they could use a hammer and a chisel and be able to hit the hammer. However, when they were doing it, he realized that he was going to hit his face shield whenever he was going to hit the hammer. Now, we're going to look at seeing, can we use a pneumatic tool, a drill or something like that, that takes that swing away that protects my face shield.
This robotic spider might be the solution NASA needs to bring home a piece of an asteroid for study. But it could open the door to a much more ambitious scheme. An army of robots flying around the solar system, grabbing hold of asteroids and diverting them off their collision course with Earth. Imagine we discover a football field-sized asteroid that's 1 year away from striking Earth. It's too big to capture in a bag. There may still be a way to avoid doomsday if we can grab onto it and push. Aaron Parness heads up a team trying to get a grip on near-Earth objects at JPL. His idea is to latch onto an asteroid the way Spider-Man clings to a skyscraper.
I started thinking about how can we take advantage of these climbing technologies for space applications. And crawling around on an asteroid is much more of a climbing problem than a walking problem. If you lose your grip, you fall off.
So Aaron and his team built Lemur, the world's first rock climbing robot. Asteroids have huge destructive power, but barely any gravitational pull. The slightest push against their surface would send you flying off into space. To come to grips with an asteroid, you have to grab it and never let go.
Go ahead and engage the grip.
Lemur's tenacity stems from its claw grippers, called microspines, designed to penetrate small holes in the uneven surfaces of asteroids. With the addition of a drill at the end of each leg, Lemur can turn itself into a rock-solid asteroid anchor.
And that's what the microspine drill does. We use one of our microspine grippers that can grip the surface of the rock, and that creates an anchor that will push into the surface.
Aaron designed Lemur as a tool to study asteroids, but he's beginning to see the part it could play in defending the Earth.
So using a drill, you also might be able to implant thrusters and anchor them to the surface of that asteroid so that you can slowly push it out of the way, so it's a near miss.
But grabbing a hold of asteroids and knocking them off a collision course with Earth takes a robot with a lot more muscle than Lemur. Lucky for us, NASA already has just the thing. It's called Athlete, or the All-Terrain Hex-Limbed Extraterrestrial Explorer.
So Athlete would be able to help in the landing on an asteroid so that we could figure out what an asteroid is made out of and how we can then best deflect it or destroy it or do any number of things to protect the Earth.
This terrestrial test version rolls on wheels. But designer Chris McQuinn is developing an asteroid model that would replace them with rock grippers.
At the end of each limb, we have a very sensitive force-torque sensor that measures all of the forces as we interact with the asteroid. We've got a pair of cameras to give an operator a very up-close view of what the limb is doing and also what the tool is doing.
Athlete could be fitted with a solar-powered ion propulsion unit aimed to blast directly away from the rocky surface. After weeks or months of gentle pushing, Athlete could change the orbit of the asteroid enough so it would no longer intercept Earth. But before it can deflect the asteroid, the robot would have to stop it from tumbling.
It's going to be a dicey situation. Asteroids move in a very complicated fashion. Sometimes they're tumbling. They often have non-uniform density, and the gravity around them can be somewhat difficult to model and predict.
Jeff Norris at JPL has been designing a system to help maneuver Athlete around tumbling, craggy lumps of space rock.
So our tools have to enable an operator, as we're approaching this complicated system, to understand not only the condition that their spacecraft is in, but what's happening on the asteroid.
His lab's visualization software has helped NASA engineers drive all the rovers on Mars this century to let them visualize where they are, where they want to go, and how to get there safely. For Athlete, he's drawn inspiration from the world of video games and has developed an immersive 3D world.
What we have here are a set of tools that we're building to control the Athlete robot. It lets me pose the robot in the position that I want it to be in, and then send commands to make the real robot do what I've commanded.
Eventually, we could have a small army of robotic defenders moving from asteroid to asteroid, slowly marshaling them out of the danger zone. And we'll have an army of humans on Earth directing those robots through video game-like interfaces.
Video game technologies are often used to make us feel like we're in some fantastic fictional place. They can also be used to connect us to very real places that are hard to get to, like an asteroid. I think what's exciting is that NASA's not sitting around waiting for these asteroids to come to us. We are the space invaders now. We're going out to meet those asteroids, to learn about them, and then to understand how best to use them and to protect the Earth.
Most of NASA's asteroid deflection plans are many years away, but this one could be ready any day. The idea is simple. Take aim at an asteroid and shoot it down.
When I was a kid, I had a telescope. And when you see the moon for the first time, you're just blown away by all the craters, big ones, small ones. And you just start imagining, if there are craters on the moon, there must be craters on Earth. And that started making me wonder, what happens if one is heading our way? Can we protect us? And if so, how do we do it? It would have to be the same thing that it would do to us. We have to hit it first.
Designing a fleet of robotic spacecraft to land on asteroids and steer them clear of Earth is still a decade or more away. What if we don't have that time? What if we see an asteroid headed our way right now? Planetary geologist Peter Schultz is working on a plan to push an asteroid out of the way with a kamikaze spacecraft.
So this is my little asteroid, and we're going to see if we can push it, shove it, just by a tiny little ball being fired into it at very high speeds, just like what we might do in space.
Except in space, the asteroid would be 300 feet wide, and this tiny pellet would be a robotic spacecraft.
We can use a small pellet because it's going so fast. And hopefully, if it goes fast enough, it'll give enough of a nudge. If we go too slow, it may not do it at all.
The Earth moves around the sun at 67,000 miles an hour. At that speed, it covers the distance of one planetary diameter in about 7 minutes. When an asteroid is hundreds of millions of miles from Earth, a nudge of a few centimeters is enough to ensure it misses us.
Imagine the mass of the asteroid relative to any mass that we're going to be sending into space to try to hit it. You know, that's like hitting a semi with a mosquito. And so we have to pick that right amount of mass, that right speed, so we can protect the Earth from the asteroid hitting us.
Peter wants to prove he can deflect the asteroid without destroying it, because blowing it to bits would be disastrous.
My biggest fear is an asteroid would actually be heading toward the Earth, and we try to stop it with an explosion or something, and it busts into thousands of pieces. Now we have all this material that's cascading into the atmosphere, like atomic bombs in the atmosphere. That would be deadly.
To replicate the speeds at which a spacecraft would be moving, Peter is using the biggest weapon in NASA's arsenal, the Ames vertical gun. It's capable of launching projectiles at over 4 miles per second, a speed that would get you from New York to LA in 10 minutes.
What we have here is what's called a two-stage light gas gun. We use gunpowder to shoot a piston down a tube that's filled with hydrogen, and we compress this hydrogen to super high pressures on the order of 100,000 psi.
All the action comes through that little port. The projectile will come zooming in at around 5 kilometers per second. You know, that's really fast. And we'll be able to watch it from cameras that are positioned there, position upstairs, and right in there.
Loading charge.
Saving Earth from an asteroid impact comes down to finding the perfect projectile velocity. Too fast, and the asteroid explodes. Too slow, and the asteroid continues on its collision course with us. Peter has set the speed of the gun to 3 miles per second, about 3/4 of the maximum.
We're set to go. We got to make sure all the cameras are triggered, ready to be triggered. Everything is automatic, but we have to be ready.
AP?
Yes.
7.3 sufficient?
Yeah, that'll work. That's good pressure.
Okay, you guys ready? Yeah, we're ready here, Chicky. Cameras are armed, ready to go.
All right, we are armed, gated, and reset. High voltage is good. Here we go. And rolling.
Oh, it got hammered.
5.12 kilometers per second.
Sweet, sweet, really nice. Okay. Oh, youch. Look at that. Oh, this is just gorgeous. And you can see all this happened in a blink of an eye. We can now see that we didn't blow it up. That's good. But what we don't know yet is if we nudge it enough. And the only way we can tell that is to look at the lower speed cameras to tell us whether or not the thing is swinging. That will give us a clue. This is slower speed, so all you see are streaks. You notice it's beginning to move. So we did save the Earth.
Peter hopes his results will help NASA dispatch a kamikaze spacecraft with just the right mass and speed to nudge a doomsday asteroid off its collision course with Earth.
You know, this could happen in any moment. This is serious stuff now. It will happen, and when it does, you want to be prepared.
But there are millions of rocks out there that could threaten the Earth. One of them is eventually going to slip through, undetected, until it's only months away from impact, and no spacecraft could reach it in time.
Your deflection technique is going to depend critically on how much time you have to actually move the object out of the way, or even break it apart. If you only have a few days, well, your options are much more limited.
There could still be a way to save millions of lives, thanks to this man, and an asteroid defense system that works at the speed of light. Asteroid impacts happen. They've crashed into Earth before. They'll do it again. No matter how much we search for them and try to push them out of the way, one day, one of them will break through those defenses and come barreling toward Earth. What could we try as a last-ditched effort to save ourselves?
In the case of that sort of, that last-ditch scenario, it's the nuclear option, literally, the Hollywood option of blowing the asteroid to smithereens. If the object is small enough, that might actually work. If it's a bigger object, the debris, the broken up bits of that asteroid are still going to impact the Earth, and so you don't want to do that.
With the nuclear weapon, or the kinetic impact, our ability to send physical objects to targets is still very primitive.
Philip Lubin and his team at the University of California, Santa Barbara believe they have something much better than the nuclear option. Although it also sounds like a plot line from a movie, Philip plans to blast asteroids with lasers and vaporize them. It's a space-based defense system called D-Star.
A laser has huge advantages in terms of its ability to rapidly engage a target at large distances long before it ever gets to Earth, or if we happen to discover one that's coming much sooner than we would like, such as the case in Russia where we had no warning.
If we spotted a dangerous asteroid 50 million miles from Earth, we might only have 100 days before impact. If we launched a spacecraft immediately, the asteroid would be at most 50 days away by the time we intercepted it. That may not leave us enough time to deflect it. But a light beam covers 50 million miles in about 4 minutes. A laser would have twice as long to push the asteroid off a collision course.
So if you wouldn't mind increasing the current level.
We're at 2.35.
So why don't we take it up to about 10 megawatts a square meter, which should be sufficient to begin the strong ablation.
He and his team are in the early stages of experimenting with how much power it takes to vaporize rock.
Laser on.
Well, this material is basalt, which is a volcanic rock, much like you would find in a real asteroid. The temperature that you're looking at right now in the spot is very close to 3,000 Kelvin. And at these temperatures, virtually all materials that are reasonable materials for asteroids will vaporize.
Laser off.
Let's see what happened with the target. I mean, actually, it looks like we've blown another pretty significant hole there.
For a laser defense system to work, it doesn't need to vaporize the entire asteroid. It only needs to turn a patch of rock into a high-speed plume of gas, acting like the asteroid's internal rocket engine.
Imagine this spewing out material. It's a rocket. It pushes the asteroid this way as the laser is hitting it from this side. And then it takes a different path so that it misses the Earth.
To reach power levels high enough to ambush a city-destroying asteroid, Philip calculates his D-Star laser defense system would need a solar panel array spanning several miles. That's far bigger than anything we've ever put into space. So Philip plans to get there slowly but surely.
A roadmap is to start small, build things which are on the order of, desktop and then room size, and work your way up.
It will be several decades until D-Star is patrolling space for asteroids, so it can't save us from one tomorrow. But Philip's students know they are closing in on their goal. It will be their generation that finally develops the technology to save us from asteroid Armageddon.
I came here because I want to make a difference in the world, and we need to come together as a community and be able to work together to come up with the most effective and efficient solution to that problem, which is the incoming asteroids.
For the past 10,000 years, human civilization has existed at the mercy of speeding space rocks. In the next 10 years, we will begin to take control of our destiny.
This is the one natural disaster that we can actually prevent from ever happening.
It's scary that these things hit, but it's empowering the fact that we can do something about it. Humans can do absolutely incredible things if they work together.
It won't be one person doing this. It's going to have to be a ton of people working very hard to understand what you have to do to protect this.
We won't be able to prevent every single disaster, but working together, astronomers, engineers, and astronauts will start to push back against these cosmic forces to show that man can prevail against the universe.